If you found this investigation through the coronal hole story, hit subscribe to Orbital View. We're tracking this event in real time as the solar wind stream makes contact with Earth's magnetosphere over the next 72 hours. Drop a comment with one word. What's your grid dependency look like where you live? On a scale of 1 to 10, how long could your household function if the power went down for a week? I read every one of those, and right now that question is more than academic. Let's get into it. 3 threads. A coronal hole the size of 30 Earths, rotating into perfect Earth-facing alignment. A solar wind stream already clocked at 700 kilometers per second, carrying a magnetic field oriented to do maximum damage to our planet's defenses. And underneath all of it, a long-term weakening of Earth's magnetic shield that almost nobody in mainstream coverage is talking about, that makes everything arriving this week hit harder than it would have 50 years ago.
There is a hole in the sun, not a metaphor, not a poetic description. A literal gap in the solar corona, the sun's outer atmosphere, where the magnetic field has opened up and is firing a continuous, high-velocity stream of charged particles directly into space. And as of this week, that hole has rotated to face Earth. Let me give you the specifics, because the specifics are what make this real. The feature that concerns solar physicists right now is a negative polarity coronal hole, meaning its magnetic field lines are pointing inward toward the sun rather than outward. That polarity detail matters enormously, and we'll come back to it. The hole spans roughly 30 solar radii in its longest dimension. To put that in terms that land in the gut, if you place this feature on Earth, it would cover an area larger than the combined surface area of North America and South America. It is not a small anomaly. It is one of the largest persistent coronal holes observed in the current solar cycle. But size alone is not the story. The story is velocity and timing. Coronal holes are the sun's fastest guns. Where normal solar wind, the constant outflow of charged particles the sun sheds continuously, travels at roughly 400 kilometers per second, the high-speed stream pouring out of a large coronal hole can reach 600, 700, even 800 kilometers per second. This event is tracking at approximately 680 to 720 kilometers per second. That is nearly 1.5 million miles per hour, and it is aimed at us. The transit time from the sun to Earth is roughly 1 to 3 days, depending on stream velocity. Based on the hole's current position and the observed wind speed, the leading edge of this stream arrives at Earth's magnetosphere within the window of this video's publication. We are not watching something approach from a comfortable distance. This is impact window territory. Now, here's where I need to slow down and explain something, because the phrase solar wind hits Earth is one of those descriptions that sounds alarming but feels abstract. The reason it matters, the reason it has ever mattered, is not radiation in the way most people picture it. You are not going to feel solar wind. It does not penetrate your skin. What it does is interact with Earth's magnetic field, and that interaction is where the real story lives. Think of Earth's magnetic field, the magnetosphere, as a bubble. Not a perfect sphere, but something shaped roughly like a comet, rounded on the sun-facing side, stretched into a long tail on the night side. The day-side boundary, where the solar wind first makes contact, sits roughly 65,000 kilometers from Earth's surface. The magnetosphere is not a wall. It is a dynamic, constantly negotiating boundary layer that deflects, absorbs, and channels the incoming particle stream. Under normal solar wind conditions, this works well. The magnetosphere deflects the bulk of the particle stream around the planet. Some particles funnel down along magnetic field lines toward the poles. That's what produces the aurora. The energy dissipates. Life continues. But when a high-speed stream arrives, particularly one with specific magnetic field characteristics, the negotiation breaks down. And what happens next is the story of this entire investigation. The instrument watching this unfold right now is the Deep Space Climate Observatory, which NASA and NOAA jointly operate. It sits at the first Lagrange point, a gravitational balance point between the Earth and the Sun, approximately 1.5 million kilometers from Earth, giving it about 15 to 60 minutes of warning before whatever it detects reaches our magnetosphere. Right now, DSCOVR is reading elevated proton flux and monitoring the interplanetary magnetic field, specifically the BZ component, which measures whether the solar wind's magnetic field is pointing north or south. That single measurement, BZ, is the most operationally important number in space weather forecasting, and we will come back to it in detail. The Space Weather Prediction Center, SPPC, operated by NOAA out of Boulder, Colorado, has issued a G-class geomagnetic storm watch for this event. The G-scale runs from G1 to G5. G1 is minor. G5 is the kind of event that ends up in the history books. Current forecasts are centered on G3, with G4 conditions possible if the BZ component of the arriving stream is strongly southward and sustained. That is not a forecast to file and forget. G3 to G4 is the zone where real infrastructure starts taking real damage. And this is where the story gets significantly more interesting. Because the question of what a G3 or G4 event actually does to the planet is not answered by looking at this storm in isolation. It is answered by looking at where the planet's defenses currently stand. And the honest answer, the answer that most coverage of this event is not giving you, is that Earth's magnetic shield has been weakening for centuries. And the rate of that weakening has accelerated. Hold that thread, we're coming back to it. Most space weather coverage skips the mechanism. It jumps from solar wind arrives to storm happens, without explaining what is actually happening at the boundary of Earth's magnetosphere. That gap matters, because understanding the mechanism is what lets you understand why some storms are catastrophic and others are forgettable, and why this one has forecasters paying close attention. The key is a process called magnetic reconnection. Picture two bar magnets facing each other with opposite poles aligned, north facing north. They repel. Now flip one so opposite poles face each other, north facing south. They attract, and if you bring them close enough, the field lines from each magnet reach across and connect. That connection is not just geometric, it releases energy. Magnetic reconnection at the magnetosphere works on the same principle, at scales and energies that are almost impossible to make intuitive. When the solar wind's magnetic field, the interplanetary magnetic field, or IMF, arrives with a southward orientation, it is pointing in the opposite direction from Earth's dayside magnetic field, which points northward. The two fields are anti-parallel, and at the magnetopause, the outermost boundary of the magnetosphere, they reconnect. This is the crack that viral social media posts keep describing, and it is worth being precise about what it actually is. Magnetic reconnection at the magnetopause is not a structural flaw in Earth's magnetic field. It is not a hole that persists and deepens and lets in more and more radiation over time. It is a dynamic, transient process that opens and closes on timescales of minutes to tens of minutes. Flux transfer events, the technical name for these reconnection episodes, are normal features of the solar wind-magnetosphere interaction. They have been observed for decades. Every major geomagnetic storm involves them. What makes this week's event potentially significant is not the existence of reconnection. It is the duration, the orientation, and the velocity of the incoming stream, because those factors determine how long and how intensively reconnection operates, and therefore how much solar wind energy actually makes it inside the magnetosphere. When reconnection opens a channel on the dayside, solar wind particles and energy don't just flood in randomly. They follow the newly connected field lines, which, like ropes being pulled, sweep around to the night side of the planet and eventually down toward the polar regions. The energy gets deposited in the ionosphere, the upper layer of Earth's atmosphere, roughly 80 to 1,000 kilometers altitude, as electric currents. Those currents are called the auroral electrojet, and the auroral electrojet is what drives the surface effects that affect infrastructure. Here's the part I want you to really understand, because it's counterintuitive. The damage a geomagnetic storm does to power grids doesn't come from radiation. It comes from magnetism changing over time. When the auroral electrojet flows, these massive sheets of current in the upper atmosphere, they create their own magnetic field. And that magnetic field fluctuates. When a magnetic field fluctuates near a conductor, like a long-distance power transmission line, it induces a current in that conductor. This is just Faraday's law of electromagnetic induction. The same physics that makes generators work also makes geomagnetic storms dangerous. The induced current is called a geomagnetically induced current, or GIC. And GICs have a characteristic that makes them particularly destructive to power infrastructure. They are quasi-DC, almost direct current. The entire alternating current power grid, the infrastructure that moves electricity across continents, is designed to handle AC. The transformers, the control systems, everything. When quasi-DC GICs are injected into that system, they saturate transformer cores. Saturated transformers overheat. Overheated transformers fail. And high-voltage transformers, the ones that step power up for long-distance transmission and back down for local distribution, take anywhere from 12 months to 3 years to manufacture and replace. That is the actual mechanism, not a satellite frying in orbit, not a dramatic pulse of radiation. A slow, invisible electrical current induced in infrastructure that was never designed to handle it, causing thermal damage that plays out over hours, not seconds. The last time a geomagnetic storm caused a major grid failure was March 13, 1989. The Hydro-Quebec power grid in Canada collapsed in 90 seconds. 6 million people lost power for up to 9 hours. Transformers across the northeastern United States were damaged. The storm responsible was a G5. This week's event is not forecast to reach G5, But I want you to understand what the mechanism looks like at full scale, because it helps calibrate what G3 and G4 mean on the same spectrum. The DST index, which measures the disturbance of Earth's magnetic field during a storm, essentially a real-time thermometer of geomagnetic activity, reached negative 589 nanoteslas during the 1989 event. For context, stormwatch thresholds begin at negative 30 nanoteslas. The threshold for the most extreme category is negative 250 nanoteslas. Negative 589 is not just beyond the scale, it is more than twice beyond the scale. There is a variable at the center of every space weather forecast that the field has spent 60 years trying to predict, has built billion-dollar satellites specifically to measure, and still cannot reliably know more than 15 to 60 minutes in advance. It is the single most important number in determining whether a solar wind event becomes a minor annoyance or a civilization stress test. The interplanetary magnetic field, the magnetic field carried by the solar wind from the sun through the heliosphere, is not constant. It fluctuates continuously. The component that matters most to Earth's magnetosphere is the north-south component, what physicists call the BZ component. When BZ is positive, when the interplanetary magnetic field is pointing northward, it is roughly aligned with Earth's dayside magnetic field. The two fields are parallel, they do not reconnect efficiently, the solar wind's energy is largely deflected. The magnetosphere holds. When BZ is negative, when the interplanetary magnetic field is pointing southward, the two fields are anti-parallel. Reconnection proceeds at the magnetopause. Energy enters the magnetosphere. The storm begins. The deeper BZ goes negative, and the longer it stays there, the more energy is deposited in the magnetosphere, and the more severe the resulting geomagnetic storm. A sustained period of Bs at negative 30 to negative 50 nanoteslas for 4 to 6 hours produces a major to severe geomagnetic storm. BZ at negative 100 nanoteslas, sustained for several hours, produces conditions approaching the most extreme events in the modern record. Reconstructions of the Carrington Event suggest BZ values that were likely off the scale of any instrument we operated in the 20th century. So why can't we predict BZ in advance? The fundamental problem is that BZ is determined by the internal magnetic structure of the solar wind plasma, and that structure is set by conditions in the solar corona and in the heliosphere between the Sun and Earth that are not directly observable. We can run magneto-hydrodynamic models of the solar wind's propagation through the heliosphere, but the specific orientation of the magnetic field at any given point in the interplanetary medium, particularly within the ejecta from a coronal mass ejection, where the field structure is governed by complex flux rope topology, is not predictable from those observations with any confidence. D-SCOVR, sitting at the first Lagrange point 1.5 million kilometers sunward of Earth, measures BZ directly as the solar wind passes it. That measurement is accurate. It is real-time. It gives forecasters the data they need to issue warnings. But it arrives 15 to 60 minutes before the same field orientation reaches Earth's magnetosphere. At most, enough time to make a phone call, execute a pre-planned procedure, and watch what happens. For grid operators, 15 to 60 minutes is enough time to take some precautionary actions. Reduce power transfers on vulnerable lines, adjust reactive power settings, prepare to disconnect certain assets if conditions warrant. It is not enough time to redesign a procedure, recruit additional operational staff, or address the structural vulnerabilities that decades of planning would be needed to fix. The one genuine solution to the BZ problem, deploying a monitoring spacecraft substantially further sunward, perhaps at L4 or L5, has been discussed in the research community for decades. The European Space Agency has studied an L5 mission repeatedly. The cost is estimated in the hundreds of millions of dollars. The benefit, in terms of warning time that allows additional precautionary actions to be taken, is real and has been quantified in multiple economic analyses. As of this writing, no such spacecraft is operational. The KP index was developed by Julius Bartels in 1939. It is a global measure of geomagnetic disturbance, specifically the range of variation in the horizontal component of Earth's magnetic field, averaged across a network of ground-based magnetometers distributed around the planet. The index runs from 0 to 9. 0 is geomagnetically quiet. 9 is the most disturbed conditions on the scale. The G scale that NOAA uses for public communication maps directly onto KP. G1 corresponds to KP5, G2 to KP6, G4 to KP8, G5 to KP9. The current watch is for G3 to G4, meaning KP7 to 8, meaning global magnetic field variation that triggers widespread aurora visible at mid-latitudes and begins to stress infrastructure systems. At G3, KP7, aurora becomes visible as far south as Oregon and Illinois in North America and across Central Europe. Satellite orientation problems begin. High-frequency radio communications experience degradation. The FAA issues advisories for polar flight routes. Voltage irregularities appear in power systems at high latitudes. At G4KP8, aurora reaches as far south as Alabama and Northern California. Widespread voltage control problems. Some protective systems on power grids trip incorrectly. Satellite drag increases measurably in low Earth orbit due to atmospheric expansion from heating. GPS accuracy degrades significantly. HF radio propagation on the sunlit side of Earth becomes unreliable. The jump from G4 to G5 is not incremental. G5 events KP9 are historically rare. The last sustained G5 event before this solar cycle was the Halloween storms of October and November 2003, which damaged or destroyed at least 14 high-voltage transformers in South Africa alone, degraded GPS accuracy to the point where some aviation systems had to revert to non-GPS navigation, and produced aurora visible from the equator. Current forecasts for this event are centered on G3, with G4 possible, depending on the magnetic field orientation of the incoming stream. The difference between a G3 event that produces spectacular aurora and a G4 to G5 event that causes infrastructure damage can come down to a single sustained period of strongly southward BZ lasting 4 to 6 hours. That is not a wide margin. And SWPC's track record on predicting BZ in advance of storm arrival is, by the agency's own public assessment, limited. The power grid. The geographic factor that matters most is the length and orientation of transmission lines. Longer lines at higher latitudes accumulate larger induced currents, and the geological substrate beneath them. Regions underlain by resistive rock, like the Canadian Shield or the Fennoscandian Shield in northern Europe, experience stronger GICs because the induced currents find it easier to flow through the conducting surface infrastructure than through the resistive ground beneath. This is why Quebec and Sweden have historically been more vulnerable than grid systems in the southern United States. NERC, the North American Electric Reliability Corporation, published updated geomagnetic disturbance standards for grid operators following the 2013 FERC order. Operators in high-latitude, high-risk zones are now required to have geomagnetic disturbance operational procedures. But the standard was designed around a benchmark event based on historical data, and the historical data has a fundamental problem. It is short. We have detailed space weather records for roughly 100 years. The sun operates on cycles that span millennia. We may be benchmarking against a dataset that has never actually witnessed the top of the distribution, GPS. The global positioning system depends on radio signals transmitted from satellites in medium Earth orbit to receivers on the ground. Those signals pass through the ionosphere. During a geomagnetic storm, the ionosphere becomes turbulent. The electron density changes rapidly and unevenly, producing what is called scintillation. Rapid fluctuations in signal strength and phase that degrade positioning accuracy. For most civilian GPS users, the practical effect of even a G3 storm is annoying rather than dangerous. Reduced accuracy, occasional signal dropout, navigation apps that briefly lose their fix. But for precision applications, centimeter-level agricultural guidance systems, survey-grade positioning, precision approach navigation for aircraft, ionospheric scintillation during a major storm can produce errors of meters to tens of meters. Satellite operations. There are currently more than 7,000 operational satellites in Earth orbit. During a geomagnetic storm, the upper atmosphere expands as it absorbs energy from the auroral electrojet. This expansion increases atmospheric drag on satellites in low Earth orbit, causing their orbits to decay faster than predicted. Satellite operators must perform additional station-keeping maneuvers, consuming precious fuel. The October 2003 Halloween storms caused operators of more than 47 satellites to enter safe mode. The Adios 2 satellite, a Japanese environmental monitoring platform, experienced a power failure from which it never recovered. Operational costs across the industry from that 2-week storm period ran into the hundreds of millions of dollars. High-frequency aviation. Polar routes are the most efficient paths between North America and Europe and between North America and Asia. Airlines flying polar routes rely on HF radio as their primary communication backup when satellite communications are unavailable. During a geomagnetic storm, the ionospheric absorption of HF signals intensifies dramatically on the sunlit side of the polar cap. Communications black out. Flights on polar routes must divert to lower latitudes. Longer flight times, more fuel burn, and schedule disruptions that cascade across global aviation networks. During the Halloween storms of 2003, more than 200 polar flight diversions were recorded over a 48-hour period. Current forecasts for this week include a high likelihood of polar route advisories from the FAA and equivalent agencies globally. Earth's magnetic field is generated by the motion of liquid iron in the outer core, a process called the geodynamo. It is not stable. It has weakened, strengthened, and reversed polarity multiple times over Earth's history. And right now, the global field is in a period of measurable, documented weakening. The most striking expression of this weakening is a feature called the South Atlantic anomaly. It is a region centered roughly over the South Atlantic Ocean and extending across South America and Southern Africa, where Earth's magnetic field is anomalously weak, significantly below the global average. The South Atlantic anomaly is a region where Earth's inner radiation belt, the Van Allen belt, dips closest to Earth's surface, because the weakened field provides less shielding. The numbers behind this are striking. Over the South Atlantic anomaly, the field intensity is roughly 24,000 nanoteslas, compared to a global average of closer to 50,000 nanoteslas in other mid-latitude regions. That is a reduction of more than 50%. The European Space Agency's Swarm satellite constellation has documented not only that the South Atlantic anomaly is expanding, but that it appears to be splitting into two distinct lobes, with a secondary minimum developing over the southwestern Atlantic near the coast of Chile and Argentina. The rate of field weakening in the region has been approximately 5% per decade since satellite monitoring began. The total intensity of Earth's magnetic dipole, the global field, has weakened by roughly 9% since measurements began in the 19th century. Paleomagnetic evidence from ancient rocks and sediments shows that the current field strength is already below the historical average for the past 10,000 years. This matters for the current storm because the magnetosphere is not a fixed structure. It responds to the solar wind based on the field that is actually there. A weaker global field means the magnetopause, the outermost boundary, sits closer to Earth under the same solar wind pressure. The shielding is not what it was. And comparing this week's event against historical event statistics requires acknowledging that the field those historical storms struck was not identical to the field this storm is striking. Earth's magnetic field is not a permanent magnet. There is no magnetized rock at the core generating a fixed field. The field is generated dynamically continuously by the motion of liquid iron in the outer core. This process is called the geodynamo. The outer core is a layer of liquid iron and nickel, roughly 2,200 kilometers thick, sitting between the solid inner core and the solid mantle. It is hot, temperatures in the range of 4,000 to 6,000 degrees Celsius, and it is in constant motion, driven by thermal convection from the heat generated at the inner core boundary and compositional convection from the solidification of the inner core. This motion of electrically conducting fluid in the presence of an existing magnetic field generates electric currents, which in turn generate magnetic fields, which sustain and amplify the motion, creating a feedback loop. The geodynamo is a self-sustaining electromagnetic engine running inside the planet. It has been running continuously for at least 3.5 billion years. The dynamo's behavior over geological timescales is documented in the paleomagnetic record. And that record shows something remarkable. The field has not only weakened and strengthened repeatedly, it has reversed polarity hundreds of times. The current field orientation, with magnetic north near geographic north, has persisted for approximately 780,000 years. By paleomagnetic standards, we are overdue for a reversal.
The honest scientific position on the current field weakening is this: it is real, measured, and consistent with patterns seen before both reversals and excursions in the paleomagnetic record, and it is not possible with current knowledge to determine which it is the precursor to.
September 1st, 1859, 5:17 in the morning, Greenwich Mean Time. Richard Carrington is at his private observatory in Redhill, Surrey, England. He is doing what he does most mornings, sketching the sunspots visible on the solar disk, projecting the sun's image through his telescope onto a sheet of white paper. He has been doing this for years. He is meticulous, patient, scientific, in a way that the 19th century occasionally produced in gifted amateurs, precise, comparative, rigorous. And then something happens that he has never seen. Two intensely bright patches of white light appear on the solar surface, near a large sunspot group. They are not artifacts. Carrington checks his instrument, checks again. The patches are real. They are brilliant, far brighter than any feature he has recorded in years of observation. He runs to find another observer to confirm what he's seeing. By the time he returns, under 5 minutes, the light has already begun to fade. What Richard Carrington witnessed on that September morning was a solar flare, almost certainly the most powerful solar flare in the modern observational record. And 17 hours and 40 minutes later, a transit time that implies a particle ejection moving at nearly 2,000 kilometers per second, the leading edge of its associated coronal mass ejection struck Earth's magnetosphere. The effects were immediate and global. Telegraph systems across North America and Europe went haywire. Operators reported that their equipment was receiving and sending messages on its own, with the telegraph lines energized by geomagnetically induced currents even when disconnected from their power supplies. Some telegraph offices caught fire. Operators were shocked by sparks jumping from their equipment. In some cases, informed and resourceful operators actually disconnected their batteries entirely and continued transmitting using only the current the storm was providing. The aurora that night was visible from the Caribbean, from Colombia, from Hawaii, from northern Australia. Prospectors in the Rocky Mountains reportedly woke in the middle of the night, convinced it was dawn because the sky was so bright. Newspapers reported that people in New England could read by the auroral light at midnight. By any measure, the Carrington Event was the most intense geomagnetic storm in the modern record. The DST index reconstruction yields an estimate of approximately negative 1,700 nanoteslas. For comparison, the 1989 Quebec event, which took down a major power grid, reached negative 589. The Halloween storms of 2003 reached negative 353. The Carrington event is roughly 3 to 5 times more intense than anything recorded in the satellite era. A 2013 study published in Space Weather by Avi Schnitzler and colleagues at Johns Hopkins University estimated that a Carrington-scale event today would cause between $600 billion and $2.6 trillion in economic damage in the United States alone. Lloyd's of London, in a 2013 risk assessment commissioned from Atmospheric and Environmental Research, estimated that a severe solar storm could leave between 20 million and 40 million people in the United States without power for periods ranging from 16 days to 2 years. I am not telling you a Carrington repeat is imminent. The current forecast does not support that conclusion. But the Carrington event establishes what the physical system is capable of producing. It happened once in recorded history. The sun is not a system that has agreed to limit itself to what it has done in recent decades. When I study the sequence of events leading up to March 13, 1989, what strikes me most is not the violence of the storm itself. It is the structure of the decision environment that the storm arrived into, and how much that structure resembles the decision environment we currently inhabit. The active region that produced the flares and coronal mass ejections in early March 1989 had been tracked and observed by solar observers for weeks. The March 6th X-class flares were not a surprise in the sense that the active region was known to be complex and energetically significant. What was not known, and what the observational infrastructure of the era could not provide, was a reliable forecast of whether the CMEs would arrive at Earth with southward or northward BZ. The forecasters at the Space Environment Center in Boulder issued a geomagnetic storm watch. Grid operators received notification. But the watch was issued on probabilistic terms. The storm might be significant, or it might not. And in the absence of specific knowledge about BZ, the rational operational response for grid operators was to monitor, not to take expensive precautionary actions that would constrain economic dispatch and might prove unnecessary. This is not a story about negligence. The operators were doing exactly what their training and procedures called for. The procedures were reasonable given the available information. The information was simply insufficient to distinguish between a storm that would be managed and a storm that would cascade. The practical question for this week's event, and for every significant space weather event in the current solar maximum, is whether the operational improvements since 1989 have matched the increase in infrastructure vulnerability over the same period. The answer requires disaggregating the question. For the existing power grid in North America and Northern Europe, the answer is probably yes. The monitoring and procedures are materially better than they were in 1989, and the infrastructure hardening, while incomplete, has reduced the most acute vulnerabilities at the highest risk locations. For the satellite population, the answer is probably no. The constellation has grown far faster than the operational space weather response capacity. For the GPS timing dependency of the financial system, the answer is almost certainly no. And for the developing world's electrical infrastructure, the answer is definitively no. There is an event in the space weather record that did not happen to Earth, but came close enough that its study has significantly changed how the research community thinks about the upper tail of the storm distribution. It is the coronal mass ejection of July 23, 2012. On July 23, 2012, a massive eruption from the Sun produced a coronal mass ejection of extraordinary velocity and intensity. The solar wind associated with this ejection reached velocities of approximately 3,000 kilometers per second, far above the already fast streams from coronal holes, and among the fastest solar wind velocities ever measured in the modern era. The BZ component of the event, as measured by the Stereo A spacecraft that happened to be in the sun-facing stream of the ejection, reached values between -50 and -100 nanoteslas, sustained for an extended period. If this event had been directed at Earth, If it had erupted 9 days earlier or 9 days later, when the same active region was in Earth-facing alignment, the resulting geomagnetic storm would almost certainly have been the most intense in the satellite era. Daniel Baker at the University of Colorado estimated that the storm would have approached or exceeded Carrington scale intensity, a dist of perhaps negative 1200 nanoteslas or below. Baker's analysis noted, if the eruption had occurred only 1 week earlier, when it was still magnetically connected with Earth, the planet would have been in the direct path of these charged particles, and the resulting geomagnetic storm may have rivaled the Carrington event. The 2012 event missed Earth by 9 days. 9 days in a solar orbit is a matter of geometry, where the active region happened to be pointing when the magnetic complexity that drove the eruption reached its peak. There is nothing special about 9 days. It could have been 5 days. It could have been 11 days. If Carrington is the worst case, Quebec in 1989 is the modern template. It is the event that gave power system engineers their clearest look at what GICs actually do to a functioning grid under operational conditions. The geomagnetic storm of March 13, 1989 did not arrive without warning. Solar observers had tracked a series of X-class solar flares starting on March 6. By March 9, NOAA's Space Environment Center had issued forecasts for a major geomagnetic storm. But the speed and the intensity of what actually arrived outpaced the forecasts. The DST index plummeted to negative 589 nanoteslas in less than 3 hours. Hydro-Quebec's power system is particularly vulnerable to GICs for reasons that are geological as much as they are engineering. The Canadian Shield, the ancient Precambrian rock formation underlying much of eastern Canada, is highly resistive. When magnetic field changes force current to flow through the Earth's crust, resistant rock deflects it toward the path of least resistance, the power system itself. Long transmission lines act as inadvertent antennas, collecting current from across enormous geographic areas and channeling it into transformers. At 2:44 in the morning, the first protective relay tripped incorrectly on the La Grande transmission system in northern Quebec. Within seconds, a cascade began. Protective systems across the network, designed to isolate faults and prevent damage, detected the anomalous GIC signals and interpreted them as fault conditions. Relay after relay tripped. Within 90 seconds, the entire Hydro-Quebec interconnect had collapsed. 90 seconds. The largest power system failure in Canadian history up to that point happened in the time it takes to read 2 paragraphs. 6 million people lost power. The darkness lasted up to 9 hours for most customers. The cascade was not caused primarily by direct hardware failure. It was caused by protective systems doing what they were designed to do, detecting anomalous conditions and isolating them, without any means to distinguish a GIC-induced anomaly from an actual fault condition. High-voltage transformers, the large oil-insulated units that step electricity up to transmission voltages in the hundreds of thousands of volts, are not mass-produced commodities. They are custom-engineered, custom-built, site-specific pieces of equipment. A large power transformer for transmission at 345 kilovolts or above can weigh 200 to 400 tons. It is manufactured to the specific voltage, current, and impedance characteristics of the circuit it will occupy. The global supply chain for large power transformers is concentrated in a small number of manufacturing facilities, primarily in the United States, Europe, South Korea, Japan, India, and China. Lead times from order to delivery have historically ranged from 12 to 24 months under normal demand conditions. The risk scenario that keeps grid engineers awake is not the loss of a few transformers. It is the simultaneous or near simultaneous loss of dozens or hundreds of high-voltage transformers across multiple grid regions, all from the same storm event. In that scenario, the global supply chain cannot absorb the replacement demand. There is no stockpile of spare units sufficient to re-equip a seriously damaged national grid. The DHS and DOE established the STEP, Strategic Transformer Reserve, program in the early 2010s. The reserve built under the program is a fraction of what would be needed to address a major geomagnetic event simultaneously affecting large numbers of units. A 2021 DOE assessment recommended expanding the reserve significantly. As of this investigation, the expanded reserve has not been funded or built. October 28, 2003. The solar activity that week was extraordinary. The active region produced 2 X-class flares in rapid succession. The first was initially classified as X17.2. The second, the following day, saturated the X-ray detectors on NOAA's GOES satellites. The actual peak intensity was later reconstructed as approximately X28, making it the largest flare in the modern instrumental record. The associated coronal mass ejections arrived at Earth in the early morning hours of October 29. The storm that followed peaked at DST negative 353 nanoteslas, severe but well short of the 1989 event. More than 47 satellites entered safe mode during the storm. The CHAMP satellite, a German geophysical mission studying Earth's magnetic field from low Earth orbit, experienced orbital decay of approximately 3 kilometers in a single day due to increased atmospheric drag from the storm-heated upper atmosphere. The Martian Radiation Environment Experiment aboard Mars Odyssey, then in orbit around Mars, recorded the highest radiation levels it had ever measured. Even at Mars, more than 300 million kilometers away, the Halloween storms were registering. Power systems in Sweden experienced a 20-minute blackout on October 30, driven by voltage instability caused by GICs. 15 transformers in South Africa experienced failures attributed to the storm, damage significant enough that South Africa's grid recovery took years. Airlines filed more than 200 polar route diversions over the storm period. The 20-minute power outage that struck southern Sweden during the Halloween storms is less famous than the Quebec 1989 event, but arguably more instructive for understanding how GIC-driven grid failures actually unfold in modern systems. Following the Quebec event, several major utilities, including some in Sweden, updated their protective relay settings to be less sensitive to the kinds of anomalies that GICs produce. The goal was to prevent the kind of false trip cascade that took down the Hydro-Quebec system in 90 seconds. But those same adjustments meant that protective systems that should have isolated a stressed section of the grid more quickly were delayed in doing so. By the time the adjusted relays did trip during the Halloween storm, the voltage excursion had propagated further through the system.
The challenge is this: the optimal protective relay response to a conventional electrical fault is different from the optimal response to a GIC event. For a conventional fault, fast tripping and isolation is almost always the right answer. For a GIC event, which is not a fault in the conventional sense, but an external forcing of the entire network simultaneously, fast tripping creates the cascade. There is no relay setting that is simultaneously optimal for both scenarios. And because GIC events are relatively rare, while conventional faults are routine, protective relay settings are inevitably calibrated primarily against the conventional fault case.
There is a claim circulating widely right now, across social media, in video thumbnails, in content that has been viewed hundreds of millions of times, that Earth's magnetosphere has developed a persistent crack or hole, that this crack is aligned with the arriving solar wind stream, and that as a result, unprecedented cosmic radiation is penetrating deep into the atmosphere and is about to cause exotic, unpredictable weather anomalies. Hyperviolent supercell storms, bizarre temperature swings that traditional meteorology cannot predict or explain. I want to address this directly and completely, because the people encountering this content deserve an honest answer. What is real? Earth's magnetosphere does develop transient dynamic connection events with the solar wind's magnetic field. These are called flux transfer events. They occur when the interplanetary magnetic field's BZ component turns southward and magnetic reconnection takes place at the magnetopause. This is documented, studied, and well understood physics. It is real. What is real? Earth's magnetic field is weakening. The South Atlantic anomaly is a genuine, documented feature of the current geomagnetic field. This is real. What is not real? The characterization of flux transfer events as a persistent structural crack or hole in the magnetosphere. These reconnection events are transient. They open and close on timescales of minutes to tens of minutes. They are not a fixed aperture. They do not represent a structural compromise of Earth's magnetic shielding in the way the viral content implies. What is not supported by evidence? The claim that solar wind ionization of the stratosphere causes severe weather anomalies, supercell storms, jet stream disruption, temperature swings, of the kind being described. Let me explain why. The Svensmark hypothesis is the honest Steelman of this claim. It proposes a mechanism linking cosmic ray flux to low-altitude cloud formation. Cosmic rays ionize molecules in the troposphere, creating nucleation sites for cloud condensation. More cloud condensation nuclei means more low-level clouds. More low-level clouds means more solar radiation reflected back to space. This is a real published hypothesis. It has been tested experimentally by the cloud experiment at CERN. The results found that while cosmic ray ionization does enhance aerosol nucleation under laboratory conditions, the magnitude of the effect is insufficient to account for significant observed cloud variability. More fundamentally, the timescale problem. The mechanism proposed in the viral content, that a solar wind event this week is going to alter jet stream mechanics and produce violent supercell storms globally over the next 7 days, is not consistent with the physics of any proposed solar weather link. Even under the most generous interpretation of the Svensmark hypothesis, the pathway from solar wind to cloud formation to jet stream displacement involves timescales of weeks to months. The jet stream is driven primarily by the temperature gradient between the equator and the poles. That gradient is determined by solar insolation, surface albedo, ocean heat content, and the distribution of land and sea. A geomagnetic storm does not meaningfully alter any of those factors on a 7-day timescale. The real story is alarming enough without the distortion. A G3 to G4 geomagnetic storm is a significant threat to infrastructure systems that billions of people depend on. And the exaggeration, ironically, makes it easier to dismiss the real threat. Because when the exotic claims fail to materialize, skepticism attaches to everything in the story, including the parts that were true. While we're in the debunking section, there is a second specific claim that circulates every time a major space weather event is in the news. It is the claim that HAARP, the High Frequency Active Auroral Research Program, a research facility in Gacona, Alaska, is either causing or amplifying the current geomagnetic activity. HAARP is an ionospheric research instrument operated by the University of Alaska Fairbanks. It consists of an array of 180 high-frequency radio transmitters capable of transmitting up to 3.6 megawatts of radio frequency power into the ionosphere. It is a real facility, it has published real science, and it is interesting in its own right. But here is the number that ends the conversation: 3.6 megawatts. A single large thunderstorm releases energy at a rate of roughly 1 billion watts, 1 gigawatt, continuously during its active phase. A major hurricane releases energy equivalent to about half the total electrical generating capacity of the United States. And a geomagnetic storm of the kind arriving this week deposits energy into Earth's magnetosphere at a rate measured in hundreds of gigawatts during the main phase. The Halloween storms at their peak were estimated to be depositing roughly 500 gigawatts into the magnetosphere-ionosphere system. HAARP's maximum output is 3.6 megawatts. The Halloween storms deposited 500 gigawatts. HAARP's entire output is 139,000 times smaller than the energy the Halloween storms were delivering. The scale mismatch is not a rounding error. It is roughly the difference between trying to redirect a river with a garden hose. And this is where the story takes a turn that most coverage of this event is completely missing. Because almost everything written and broadcast about this week's coronal hole event is framing it as an isolated incident, a solar weather episode that will run its course over 3 to 5 days and then recede. That framing is not wrong, exactly. For this specific event, that trajectory is the most likely outcome. But it misses something fundamental about where we are in the Sun's 11-year activity cycle. We are currently in solar cycle 25. Solar maximum was initially forecast by NOAA's Solar Cycle 25 prediction panel to occur around 2025, with a relatively modest peak similar to cycle 24, which was a historically weak cycle, with a peak sunspot number of 116, significantly below the 20th century average. It was wrong. Solar cycle 25 has vastly outperformed predictions. By 2023, the actual sunspot numbers were tracking far above the forecast envelope. The actual peak, based on smooth sunspot data, appears to have arrived in late 2024 with a monthly smooth sunspot number that has not been seen since solar cycle 22 in the early 1990s. What this means operationally is that we are at or very near the most active phase of a more active solar cycle than almost anyone predicted. And the most active phase is also the period when the largest, most dangerous events are most likely to occur. Consider the satellite population. When the Halloween storm struck in 2003, there were roughly 700 operational satellites in Earth orbit. Today there are more than 7,000. The proliferation of low Earth orbit megaconstellations has created an infrastructure that is extraordinarily valuable, deeply embedded in global communications and internet access, and concentrated in the altitude bands most sensitive to orbital decay during geomagnetic storms. A Carrington-scale event today would interact with a satellite population 14 times larger than the one that existed during the last major storm. Consider GPS dependency. In 2003, precision GPS was an emerging technology used by specialists. Today, it is load-bearing infrastructure. Financial systems use GPS timing for transaction synchronization. Power grids use GPS timing for phase measurement units. Cellular networks use GPS timing for base station synchronization. The surface of GPS dependency in the global economy is incomparably larger today than it was during the last major storm. Starlink alone, as of this writing in 2026, operates more than 5,000 active satellites in low Earth orbit at altitudes between approximately 330 and 560 kilometers. This is the altitude band most sensitive to atmospheric drag during geomagnetic storms. In February 2022, SpaceX launched 49 Starlink satellites into their initial deployment orbit of approximately 210 kilometers altitude. That launch occurred during the onset of a minor geomagnetic storm, G1, the lowest significant level on the scale. The storm heated the atmosphere, expanding it into the orbital altitude of the newly deployed satellites. Atmospheric drag increased dramatically, up to 50% higher than predicted. 40 of the 49 satellites failed to raise their orbits and re-entered the atmosphere within days. SpaceX lost 40 satellites to a G1 storm. Under a G4 or G5 storm at solar maximum, the thermospheric expansion at low Earth orbit altitudes would be substantially more severe. The operational coordination challenge of managing thousands of satellites in various stages of storm response safe mode, orbital adjustment, and system restart is not something that has ever been practiced at scale under actual storm conditions. Modern digital infrastructure runs on time, not approximately, precisely. The synchronization of financial transactions, the coordination of cellular network handoffs, the phase measurement units that monitor power grid stability, the timestamping of data packets across the internet. All of this requires timing accuracy that is typically measured in nanoseconds or microseconds. And the dominant source of that timing globally is GPS. During a major geomagnetic storm, the ionosphere becomes turbulent. Equatorial plasma bubbles, large-scale electron density irregularities that form in the equatorial ionosphere, create scintillation conditions that can degrade or sever GPS signal reception entirely. A receiver that loses GPS lock during a geomagnetic storm does not simply display a reduced accuracy position. It may lose its timing reference entirely. In modern high-frequency trading environments, timestamp accuracy requirements are measured in microseconds. A GPS timing receiver that loses lock falls back on its internal oscillator. These fallback oscillators are accurate, but they drift. After a few minutes, the timestamp error may be in the range of microseconds. After longer periods, it may reach milliseconds. In systems designed around very tight timestamp synchronization, accumulated timing errors can trigger anomaly detection systems that flag transactions as potentially fraudulent, suspend processing pending audit, or initiate automatic halts. A National Academy of Sciences study published in 2022 found that GPS timing dependency in financial infrastructure was one of the least documented and least understood systemic vulnerabilities in the space weather risk landscape. The study recommended a systematic mapping of GPS timing dependency across financial systems and the development of enhanced fallback standards. As of this investigation's writing, that recommendation has not been acted on comprehensively. A polar route between Chicago and Beijing covers roughly 10,000 kilometers. It crosses the Arctic above approximately 70 to 80 degrees north latitude for a substantial portion of its length. High-frequency radio communication is the primary communication method for large portions of polar routes, where satellite coverage is geometrically limited. During the ionospheric disturbance phase of a major geomagnetic storm, HF radio on the polar cap becomes unreliable to unusable. The mechanism is polar cap absorption. Energetic protons accelerated by the solar wind and deposited in the polar ionosphere create an absorbing layer that attenuates HF signals. During major events, it can reach levels that completely block communication, even with maximum transmitter power. A Chicago to Beijing polar route diversion might add 3 to 4 hours of flight time and several tons of additional fuel. But the cost of losing communication with an aircraft over the polar cap, of having no means to issue updated clearances, weather advisories, or emergency instructions to a flight carrying 200 to 300 passengers over one of the most remote environments on Earth, is not acceptable under any reasonable operational standard. During the Halloween storms in 2003, more than 200 polar route diversions over approximately 48 hours produced scheduled disruptions that cascaded for days. The direct cost to airlines was estimated at tens of millions of dollars. The ISAO Space Weather Center, which began formal operations in 2020, represents a genuine improvement in international aviation space weather coordination. But the fundamental vulnerability, loss of HF communication over the polar cap, cannot be solved by better advisory products. It is a physics limitation. The discussion of GPS degradation during geomagnetic storms typically focuses on high-latitude effects. But there is a second category of GPS degradation, equatorial plasma bubbles and associated scintillation, that occurs in a completely different geographic region through a different mechanism, and that is in some ways more disruptive to GPS-dependent operations because it affects the most densely populated and economically active latitudes. Equatorial plasma bubbles are large-scale structures that form in the equatorial ionosphere, primarily in the post-sunset hours. During a major geomagnetic storm, the energy deposited in the high-latitude ionosphere propagates toward the equator as equatorial electrodynamics are disturbed. This disturbance enhances equatorial plasma bubble formation. More bubbles, larger bubbles, more severe scintillation. The geographic regions most affected include Equatorial Africa, the Indian subcontinent, Southeast Asia, Brazil, and Equatorial South America. These are not low GPS dependency regions. India and Brazil have major and rapidly growing precision agriculture sectors, mobile payment infrastructure, and logistics networks that are increasingly GPS dependent. The broader point is that GPS scintillation during a major geomagnetic storm is not a high-latitude problem. It is a global problem, and the populations most affected in the equatorial scintillation zone are often the populations with the least alternative infrastructure, the communities most dependent on GPS-based services, precisely because they lack the physical infrastructure that GPS was designed to supplement. At SWPC in Boulder, the 24-hour operational center is running on heightened watch status. The forecaster on shift are monitoring DSCOVR data in real time: BZ, solar wind velocity, proton flux, electron flux. The alert system has 3 levels: watch, days in advance, warning, within an hour of expected onset, and alert, ongoing conditions. Each level triggers different operational responses from different customers. Grid operators receiving a G3 watch will typically convene their space weather coordination teams, review their geomagnetic disturbance procedures, identify which transmission assets are most vulnerable, and prepare to execute reactive power management adjustments if the storm materializes as forecast. Satellite operator receiving a G3 watch will typically review their constellation's current orbital parameters, identify which satellites are in vulnerable configurations for the South Atlantic anomaly crossings, prepare to place sensitive instruments in safe mode, and assess whether any preemptive orbit adjustments make sense given fuel constraints. These are mature professional responses to a known threat. For a G3 to G4 storm, the current forecast, they are likely adequate to prevent major infrastructure failures. But there is an important caveat. All of these procedures were designed, calibrated, and validated against the storm history of the satellite era, roughly the last 60 to 70 years. They have never been tested against a Carrington scale event. In May 2024, Earth experienced the most intense geomagnetic storm since the Halloween events of 2003. A series of powerful coronal mass ejections arrived at Earth between May 10th and May 13th. The resulting storm reached G5, the maximum on the scale, making it the first G5 storm since the Halloween events more than 20 years earlier. The DST index reached approximately -412 nanoteslas during the main phase. Aurora was visible across large portions of the United States, Europe, and Australia, from Florida, Texas, and Hawaii, latitudes where the phenomenon is essentially unknown under normal conditions. The infrastructure impacts were measurable, but in most cases, manageable. Power grids in the northern United States and Canada reported GIC events. No major grid outages attributable to the storm were reported in North America. Grid operators had executed their geomagnetic disturbance procedures. The procedures worked. The May 2024 event demonstrates that the procedures and systems developed since 1989 work under significant geomagnetic stress. It also demonstrates that G5 conditions are possible in the current solar cycle. But it says nothing about what happens at Carrington, -500. The May event reached -412 nanoteslas. Carrington reached -1,700. The gap between those numbers has never been tested against modern infrastructure. DSCOVR's real-time solar wind data is available through NOAA's Space Weather Prediction Center website at swpc.no.gov. The real-time solar wind plots show B's solar wind speed, proton density, and total field intensity, updated every minute. If you go there during the arrival window and watch BZ, you are watching the single most important variable in real-time geomagnetic storm forecasting. When BZ goes negative and stays negative, the storm's main phase has begun. The KP index, updated every 3 hours by NOAA and by the GFZ German Research Center for Geosciences in Potsdam, tells you the current global geomagnetic activity level in a single number. KP7 or above means G3 conditions. KP8 or above means G4. KP9 means G5. The DST index, which gives a finer-grained picture of the storm's main phase intensity, is computed and published by the World Data Center for Geomagnetism in Kyoto, Japan, with a typical latency of 1 hour for quick-look data.
For aurora chasers, anyone within the potential aurora visibility zone, which, during this event, extends well into mid-latitudes, the NOAA Aurora Forecast Oval Map, also on swpc.noaa.gov, shows the predicted extent of aurora visibility updated in real time. All of this is verifiable, publicly accessible, and right now, during the arrival window of this specific event, actively informative. You do not need to take anyone's word for what is happening. The data is there.
I want to present this investigation's evidence to you through three honest interpretations, because the data genuinely supports more than one reading, and because I think you deserve to see them all laid out rather than have me pick one and present it as settled. Interpretation 1. The reassuring case, the current G3 to G4 geomagnetic storm forecast, represents a known, manageable risk that the global space weather operational community is well prepared to handle. The procedures developed since the 1989 Quebec event have been continuously refined and tested against multiple significant events, including the G5 storm of May 2024. That event, the most severe in more than 20 years, produced no major grid failures in North America because operators had executed their geomagnetic disturbance procedures effectively. GPS degradation occurred but was within tolerable bounds. Satellite operations experienced manageable disruption. This outcome was not luck. It was the result of serious engineering, serious operational planning, and serious institutional learning. Under this interpretation, the weakening of Earth's magnetic field, while real and documented, is a gradual multi-century process that does not meaningfully change the risk calculus for any individual storm event. Solar cycle 25, while stronger than predicted, is not unprecedented in the context of the 20th century solar record. It is comparable to cycles from the 1950s through the 1990s, a period during which no civilization-altering space weather event occurred. This interpretation is not wrong. It accounts for the actual data. A serious, informed person can hold it. Interpretation 2, where the literature points the G3 to G4 event this week, is best understood as an event drawn from a probability distribution with a long tail that our operational infrastructure was not designed to handle. The current storm is likely to be managed adequately. But likely to be managed adequately and the risk is acceptable are different statements. The research literature on Carrington scale event frequency is not comforting. A 2012 study published in Space Weather by Pete Riley at Predictive Science estimated the probability of a Carrington scale event in any given decade at approximately 12% based on the statistical distribution of historical storm intensities. Even the lower bound of the uncertainty range, roughly 3% per decade, represents a roughly 30% chance of a Carrington scale event in any 50-year period. Under this interpretation, the weakening magnetosphere matters. The expanding satellite population matters. The deepening GPS dependency of critical infrastructure matters. These are not catastrophist embellishments. They are documented features of a risk landscape that has been getting more complex and more consequential for decades, during a period when the threat has been treated primarily as an interesting scientific phenomenon rather than an engineering and policy priority. Interpretation 3. The most concerning physical possibility. The current combination of factors, solar cycle 25 outperforming predictions, the expanded and GPS-dependent modern infrastructure, the weakened magnetosphere, and the absence of any operational playbook that has been tested against extreme events, represents a genuine civilizational vulnerability that is not adequately priced into current policy or investment decisions. A Carrington-scale event striking the current infrastructure landscape would not produce the same effects as the original Carrington event, which damaged telegraph infrastructure that could be repaired in days. The Lloyd's of London estimate $600 billion to $2.6 trillion in economic damage in the United States alone was published in 2013, before the dramatic expansion of the satellite population and GPS dependency of the last decade. The current exposure is larger. Under this interpretation, the most concerning specific scenario is a complex active region producing multiple CMEs in rapid succession, with the second or third eruption arriving while the magnetosphere is still compressed and stressed from the first. This scenario, which solar physicists call an interacting CME event, can produce storm intensities that exceed what any single eruption would produce. The 1989 Quebec event was driven partly by this kind of compound arrival. The cost of the first interpretation being wrong, of the risk being greater than manageable, is civilizational. The cost of the third interpretation being wrong, of the risk being less than civilization threatening in our lifetime, is the cost of infrastructure investment and operational preparation that improves resilience to multiple threats, not just space weather. Those are not symmetric costs. And that asymmetry is, in my view, the core argument for treating space weather preparedness with more urgency than current policy reflects. The Lloyd's of London report, published in 2013, found that a Carrington-scale event could cause between $600 billion and $2.6 trillion in economic damage in the United States, with the enormous range reflecting uncertainty about transformer failure rates and cascading economic effects. A subsequent risk assessment by the Cambridge Center for Risk Studies, published in 2015, estimated the economic impact of a Carrington scale event in the range of $2.5 to $3.4 trillion globally for a 4-day blackout scenario, rising to potentially $5 to $8 trillion if the blackout extended for several weeks due to transformer replacement delays. A COVID-19 scale impact, compressed into weeks, driven by physical destruction of irreplaceable infrastructure rather than economic disruption alone. When the reinsurance market exits a risk category, it is not always because the risk is too small to price. Sometimes it is because the risk is too large. The systematic exit of reinsurers from geomagnetic storm coverage is a market signal about how the people who are paid to assess catastrophic risk have priced this one. What is confirmed? Coronal holes produce high-speed solar wind streams. The current coronal hole has rotated into Earth-facing alignment. The solar wind stream is in transit. NOAA has issued a G3 storm watch. Historical events demonstrate that G3 to G4 storms cause measurable infrastructure effects across power grids, GPS, satellite operations, and aviation. Earth's magnetic field is weakening at a documented measured rate. Solar cycle 25 is stronger than predicted. What is uncertain? The peak storm intensity depends on the BZ component that will only be fully characterized by DSCOVR data in the minutes before arrival. The probability of a Carrington scale event in the current solar cycle is genuinely unknown, with estimates ranging across more than an order of magnitude. The degree to which the weakening magnetosphere amplifies surface effects of any given storm is not well constrained by the current research literature. What specific data would change this picture? A detailed public release of GIC monitoring data from the May 2024 G5 storm, which would allow independent assessment of how close to critical thresholds the high-latitude power infrastructure actually came. A systematic public assessment of high-voltage transformer vulnerability and replacement lead times, which has been called for repeatedly by independent researchers, but has not been undertaken at the national level in a form that allows independent review. In 2016, the Obama administration issued a National Space Weather Strategy and Action Plan, the first formal statement at the presidential level that space weather was a national security and critical infrastructure priority. The Trump administration did not rescind it. The Biden administration issued an updated version in 2019. On the monitoring side, DSCOVR remains the primary solar wind monitoring satellite. Plans for a DSCOVR successor, a mission that would provide redundant solar wind monitoring and potentially longer warning time, have been in development for years without a launched replacement. If DSCOVR were to fail during this solar maximum, the warning time for geomagnetic storms would revert to the GOES satellite data, which provides less comprehensive solar wind characterization. On the transformer reserve side, the STEP program has built a modest reserve of spare large power transformers. The reserve is useful for localized events, but is not sized for a major Carrington scale event. A 2021 DOE assessment recommended expanding the reserve significantly. As of this investigation, the expanded reserve has not been funded or built. This is not a story of governmental failure in any dramatic sense. It is a story of a risk that is real, recognized, studied, documented, and partially addressed, but not addressed at the scale and urgency that the scientific community's assessment of the risk would warrant. The scientists who study solar-terrestrial interaction have been remarkably consistent over the past 2 decades in what they say publicly about the long-term risk picture. The consensus view is approximately this: extreme geomagnetic storms are not anomalies. They are expected features of the solar cycle that occur with calculable, if uncertain, frequency. The 20th century's track record of not producing a Carrington-scale event in a world with extensive electrical infrastructure is not strong evidence against the risk. It is a sample size of 1 solar century in a system with behavior documented on millennial timescales by paleomagnetic proxies. The vulnerability of modern infrastructure to extreme events has grown substantially over the past 3 decades and continues to grow. The infrastructure hardening measures enacted since 1989 are real and meaningful. They have almost certainly prevented significant damage in several events since then, but they are not designed for events at the upper end of the physical range. And the current solar maximum, stronger than predicted, occurring in an infrastructure landscape fundamentally more vulnerable than the landscape of the last comparable solar maximum in the late 1990s, represents the highest exposure period the modern technological civilization has yet encountered. The space weather risk conversation in the United States is sometimes discussed as if it is primarily an American concern. It is not. High-latitude regions, Canada, Scandinavia, Russia, the northern United Kingdom, have historically been most vulnerable to GSE effects, and have, to varying degrees, developed GSE monitoring capabilities and some hardening measures. But the developing world's infrastructure vulnerability has received almost no attention in the space weather risk literature. South Africa's experience during the Halloween storms, 15 transformer failures, years of recovery, is the clearest documented example of what this risk looks like in a developing world context. South Africa had a more established grid than most of sub-Saharan Africa. The countries with less robust infrastructure, less financial resilience, and less institutional capacity represent a global equity dimension of the problem that the existing risk literature has largely not addressed. For billions of people whose electricity access depends on infrastructure that was not built to any geomagnetic disturbance standard, a Carrington scale event is not a resilience challenge. It is a potential humanitarian catastrophe. When researchers like Pete Riley estimate a 12% probability of a Carrington scale event per decade, they are working from a specific methodology, fitting a statistical distribution to the frequency-magnitude relationship of geomagnetic storms in the observational record and extrapolating to the extreme end. The first limitation is the sample size problem. The modern instrumental record covers roughly 100 years. In that period, we have observations of perhaps a dozen major to extreme events. The extremes of the distribution are constrained by very few events. Riley's 12% estimate has an uncertainty range that spans from a few percent to perhaps 30% per decade. The second limitation is whether the statistical distribution is stationary. If the current solar maximum is part of an upswing in longer-term solar activity, as some researchers have proposed based on the carbon-14 and beryllium-10 records in ice cores, the probability of extreme events in the current period may be higher than the century-scale average. The honest summary: the chance of a Carrington scale event in any given decade is probably somewhere between 3 and 25%. The uncertainty is irreducible with the data currently available. The expected value, the probability-weighted cost of the risk, is high enough that any reasonable cost-benefit analysis supports substantial investment in preparation, even under the most optimistic assumptions about event frequency. I want to end this investigation by telling you what happens next, because this story does not close when the solar wind stream passes. Over the next 72 to 96 hours, the arriving stream will interact with Earth's magnetosphere. DSCOVR will measure the BZ, SWPC will issue its warnings, grid operators will execute their procedures. Aurora chasers across the northern and southern hemisphere will watch the skies. And then, almost certainly, based on current forecasts, the storm will pass, KP will descend, the DEAST will recover. The atmosphere will settle. GPS will return to normal accuracy. But the background conditions will not have changed. The coronal hole will rotate away from Earth-facing alignment and will eventually return. Another active region will rotate into view. The solar maximum will continue to produce elevated activity through the remainder of this solar cycle. The magnetosphere will continue its documented gradual weakening. The satellite population will continue to grow. The infrastructure dependency on GPS timing will continue to deepen. For this specific event, if you depend on GPS-based navigation for something time-sensitive, be aware that accuracy may be degraded during the main phase of the storm, particularly in the evening hours at mid-latitudes and in equatorial regions. If you operate radio communications on HF frequencies and you use polar paths, monitor SWPC advisories. For most people, the practical action is: enjoy the possibility of an unusually spectacular aurora display if you are in a mid-latitude region, and watch the real-time SWPC data at swpc.ano.gov if you are interested in following the event as it unfolds. The storm will not end the world. For the long-term structural risk, the honest answer is that individual preparation matters at the margins, but the meaningful risk management has to happen at institutional and policy levels. The transformer supply chain problem, the GPS timing dependency of financial infrastructure, the satellite megaconstellation vulnerability, these are not problems that individual preparation addresses. They require sustained institutional and policy attention. What individuals can do is be informed and be the kind of voter and citizen who demands that the people responsible for these systems treat the risk with the seriousness it deserves. The science is there, the risk assessments are there. The gap between what is known and what has been done is documented and public.
The infrastructure that runs your life is downstream of a star that operates on timescales that make our entire recorded history look like an afternoon. What we know about what that star can do is limited by a century of instrumental observation and a few millennia of proxy evidence. What we don't know is, by definition, everything outside that window. We'll be watching, and when this story moves, in whatever direction the evidence takes it, we'll be here.